Greetings from the night in the forest. I'm Dr. Wallace Vosloo, and for me it's an honor to be part of SonSA Energy Conference today. I will be sharing some thoughts on the world perspective on energy, and without any further ado, let's get going. Energy on Earth comes from hydrogen, nuclear fusion reactions taking place in the core of the sun under immense gravitational pressure, and this basically produces the heat which is radiated out from the sun. Yeah, it's hydrogen is the fuel source. Nuclear fusion is the process. Uh-huh. All energy on Earth comes from nuclear fusion or derivatives thereof, and the fuel source is hydrogen. Yeah, get over it. So the sun basically radiates out an electromagnetic energy spectrum, which takes about 8.3 minutes to reach the Earth at about 300,000 kilometers per second. And this spectrum has got different wavelengths, and you would find that it's made up of what we would define under the different types of wavelengths as gamma rays and X-rays and ultraviolet, visible and infrared light. And then you're looking at microwaves and lower frequencies down to long radio waves and so on. But at the end of the day, this spectrum of different wavelengths are then radiated out from the sun. Now, how does this lot reach the Earth? Because now you've got this spectrum there and you've got it all fantastic being radiated out, but it now needs to reach the Earth. And light is basically made up of photons, and photons are the energy carriers. And so you find that the energy of a photon is very much determined by the wavelength of that photon. And so the energy is transferred down to the Earth by photons. And these photons of different wavelength with different energy levels then reach the Earth. Photons transports the electromagnetic energy down to Earth, and the full spectrum of this electromagnetic energy is available at the exosphere. And from there, the different layers surrounding the Earth filters out part of the spectrum. And what is finally available at the surface of the Earth, which we can use, is in the optical window, looking at UVA, we're looking at the visual light, obviously, and near infrared. So that is what's available for use on the surface of the Earth. Now, the core of the Earth itself is a solid core, and it's got magma surrounding it. And in that core, the magma part of the core, we have nuclear decay. Yes, nuclear decay. And that is basically adding approximately 50% of the energy that is generated or that is inside the Earth. And we're looking at temperatures which is very close to the surface of the sun at 6,200 Kelvin. And the pressures, which is immense, we're looking at about 3,64 megabar, very high pressures. So yes, folks, all energy which we have available on Earth comes from nuclear reactions, hydrogen as the fuel source on the sun, and with fusion taking place, nuclear fusion taking place, and on Earth itself, we receive that energy, and it's normally here in the optical window, and at the same time, inside the core of the Earth, we're finding nuclear reactions taking place there, which is also adding to our energy source, which we have available on Earth. Climate change. Yep, that is what's basically driving us from making use of fossil fuels to renewables. Not a bad idea in the sense that it's basically going to reduce our pollution levels on Earth. The temperature which the guys are predicting, if we do not get rid of carbon dioxide and greenhouse gas emissions, is we're going to be looking at about a rise to 4 degrees above the norm, even up to 6 they are predicting. And this is the big scare. And the sea levels will be rising, and the climate on Earth will be radically affected by this temperature change. Now, if we take a look at the history of temperatures on Earth and we look at ice core samples, temperature levels which has been determined along with carbon dioxide levels at that time, and we work back in hundred thousands of years, you'd see that the Earth has got a cycle where there are ice age periods, and then there's periods where we have high temperature or temperatures above a norm. And you can see we've got areas here which is about 4 degrees above the norm, which correlates to carbon dioxide samples taken in the same ice core. And so we can see that the Earth, it's a natural cycle for the Earth to change temperature. And also at the same time, there's been some major changes on Earth that's taken place. Now, if we take a look at predicting the weather on Earth, we can't do that for longer than, more than 7 days into the future. So the question is asked really, can we do these predictions accurately, which they are claiming? The world uses in the order of 18.5 terawatt year per annum. So that's quite a bit of energy. And South Africa, we are looking in the order of about less than 1% of that total per year. And that gives you an indication of the amount of energy that is used, and it's represented by this little ball. Now, everything on this presentation is according to scale. So that little ball tells you how much energy is used per annum. Now, we have finite energy deposits available on Earth. That means stuff that is in the Earth, but it gets used up and it does not get more. We might discover new deposits and then it might grow slightly, but we end up that at this stage, we're looking at about 830 terawatt years of coal. So if we use 18.5 terawatt year per annum and we take 830 terawatt years that we have available and we only relied on coal, then we can work out that we don't have 100 years left. If we combine it with uranium, and you can see that uranium, there might be much more available from nuclear than what we thought, and we're looking at about 185 terawatt year. And petroleum products, which is typically our oil resources and so on, we're looking at 335 terawatt years. And on natural gas, we're looking at 220 terawatt years. Folks, when we add these all together and we take a look at what is the usage per annum, and we only rely on these resources which are available on Earth, which we are slowly but surely depleting, we don't have much left. So we have to move across to something else where we get our energy from. And that, I think, is why we have this big shift of moving away from fossil fuels to renewables. And it's not just the scenario of climate change, it's a scenario that if we continue the way we're going, we're not going to have anything left to use. So the big move is towards making use of the biggest energy supplier on Earth, and that's solar. And that we know comes from the sun and nuclear reactions on the sun and from hydrogen. So solar, if we look at this big yellow disk which we're sitting here, that is what the sun delivers to the earth per year. So it's more than what is available in the earth itself, and that is per year. It's amazing. So we will have to move towards making use of solar energy. The derivatives of solar energy is a whole array of other issues which we can use. For instance, wind. Wind is a renewable, and wind is deposited on the earth, or is available on the earth in 70, 100, around about 100 terawatt years per year. So it's not something that disappears. It's renewable. And so wind is actually created by the sun, by temperature differences. Waves at the same time is very much created by the wind, and it also at the same time is associated with tidal movements and so on, which is also influenced by the moon. But then we have inside the earth where we have also nuclear reactions, and where we got a lot of temperature which is kept inside the earth. We have geothermal, and the potential for geothermal is large if we make use of geothermal. But then at the same time, we are looking at tidal energy that's available. We're looking at hydro potential that's available, biomass, and yes, then we've got the ocean thermal energy conversion side of things. And when you put this whole lot into perspective, you can see that we actually have quite a lot of renewable possibilities which we can use as our energy sources. Right, let's take a look at volumetric versus gravimetric energy density of some of our most important energy carriers, which is available to us for use on Earth. And immediately we can see that the best performer is nuclear fission. And if we go for nuclear fusion, that's on the sun, it's off the graph. So that's a no-brainer. Nuclear is definitely our top product. Then we take a look at hydrogen at different pressures and in liquid form, and even in a form of ammonia is brilliant. It's excellent. And if we look at it in the form of ammonia, it compares very well with our other fuels which we have available, for instance, like LP gas, crude oil, and diesel. And we find that we use petrol and diesel for our vehicles. And the reason for that is that it's got an excellent energy density, and it's a very good energy carrier. Now, currently, we're making quite a lot of use of lithium-ion batteries for storage, and the guys are looking at molten salts and hot water and flywheels and lead acid and so on. And then at the same time, compressed air and superconductors. We're using hydro, and when we compare this lot to hydrogen, we find that hydrogen is outperforming from a energy density and as an energy carrier the rest. Take a look down here. Here is the wind. If we're looking at wind, it's not really a very good energy density energy carrier, and hydro is here. Well, game-changing technologies for energy. At this stage, a report that's been generated by Itonics gives us a view of what's going on currently in the world. And if we take, for example, the next generation of PV and what is being developed surrounding that, well, firstly, if we take a look at the spectrum coming down from the sun, we don't really fully utilize that full spectrum in PV cells. So definitely there's going to be a move towards more efficient and better harvesting of the energy coming down towards the earth. Then if we place it into the outer atmosphere, we would be able to also capture the full spectrum and also at higher intensity levels. Then at the same time, they're looking at hydrogen storage, which we now know why. And at the same time, we're also looking at a next generation of batteries, which is going to obviously include hydrogen. And then the guys are also developing some organic electronics and also looking at harvesting um, other energies from surrounding environments. And at the same time, they're looking at distributed energy resources, where you're basically looking at using your and generating your energy in the same area. So you're going to be having hybrid systems being built very close to the user. And there, the technology of making use of a nuclear pebble bed reactor along with your renewables can combine to supply a very sturdy and good energy option to the local community. The future lies in using our natural resources, which are still available on Earth, sparingly. We'll have to move towards renewables, guaranteed. Our fuel is going to be hydrogen. It's the most efficient way of doing it. We're going to be driving our cars on hydrogen, trucks, planes, large ships. Hydrogen is going to be the fuel of the future. We're going to find that we'll have to use the full spectrum of electromagnetic energy coming down to the Earth and not limit it to what's available on the surface of the Earth, but must probably move out and put up solar capturing and energy capturing devices in outer space and transferring that energy down to Earth through different portholes, electromagnetic energy portholes, where we then can conductorless send this energy down. We'll have to think about using our abundance of seawater to create hydrogen, making use of that solar energy along with a small little micro bio nano little engine, which then is driven, getting its energy from the sun, and then basically takes the seawater and creates it into a hydrogen fuel which we can use. And we should not forget that nuclear is our friend. And we're going to need nuclear to ensure that we have stable networks. So you do need nuclear. And we will have to continue to make use in the interim of coal and gas. We don't have an option. Then we must not forget about the energy which is captured inside the earth and that we can make use of geothermal to be able to harness that energy. And for instance, along the South African coast, there's the Agulhas current that is running. And that current is moving continuously at a certain speed. And if you put two electrodes in a magnetic field there, you can capture the energy, but because the seawater is a conductor, and if it moves through a magnetic field, it generates electricity. Or you can make use of underwater turbines. So we need to think lateral. And the secret by thinking lateral and getting things achieved is to make the problem, the thing that's standing in your way, part of the solution. And if you do that, you'll be surprised what you can get right. So don't make the problems a big issue. Think about making and using those problems as part of the solution. And folks, only the person in the mirror with creative ideas and with a lot of oomph can make this happen. So I'm really looking forward to see how South Africans are going to come and actually come up with creative ways and ideas to resolve this whole energy problem, which we have not only in South Africa, but throughout the whole world. And as you can see, we have to do something. We'll have to move towards renewables because we don't have enough fossil fuels and other energy available in the earth that can sustain us for the next century. It's not there. And with that, I would like to conclude my presentation and thank you very much.